Imagine a future where a single breakthrough computer can unlock years of encrypted data overnight. In this module, we'll look at how quantum computing threatens today's cryptography, and what that means for HSMs, PKI, and the long-lived trust services your organization relies on. To see why quantum computers are a problem for cryptography, we need one core idea. Classical computers use bits. Each bit is firmly a 0 or a 1, like a coin lying flat as heads or tails. Quantum computers use qubits. A qubit can be in a mix of 0 and 1 at the same time, like a coin spinning in the air. This superposition lets a quantum computer explore many possibilities in parallel, which is what enables new types of attacks. Quantum attacks don't affect every type of cryptography in the same way. Shor's algorithm is the big one. It efficiently solves the hard math problems behind RSA and elliptic curve schemes. That means any system relying on those public key algorithms would eventually be breakable, no matter how large the key size. Grover's algorithm is different. It speeds up brute force searching, which weakens symmetric encryption and hashes, but doesn't destroy them. We can compensate by roughly doubling key sizes, for example, preferring AES 225.6 over AES 20.8 for long-term protection. This matters because almost everything we use for secure communication rides on RSA, Diffie, Hellman, and elliptic curve cryptography. Quantum computers don't just weaken these algorithms. At scale, they break the hardness assumptions they depend on. If that happens, protocols like TLS and VPNs and digital signatures on software and documents could effectively become transparent overnight. The idea of harvest now, decrypt later explains why quantum risk is already real. Attackers don't need a quantum computer today. They can copy encrypted traffic or files now and store those ciphertexts cheaply for years. Once practical quantum computers arrive, the same stored data can be decrypted in bulk, retroactively breaking confidentiality. This is especially serious for information with long-term sensitivity: government records, health data, trade secrets, and legal documents. So crypto migration isn't really about some future year. It's about protecting what you're sending and storing right now. This leads to a simple timeline equation. Your data has a shelf life, the period during which it must remain confidential or trustworthy. You also need lead time to migrate your systems to quantum-safe cryptography. If the data's shelf life plus your migration time is longer than the time until practical quantum attacks, that data is effectively at risk today, even though large-scale quantum computers don't yet exist. Within that equation, trust services and PKI sit in the highest risk part of your infrastructure, because they act as the root of trust for everything else. If an attacker compromises a root CA or a code-signing HSM, they don't just break one system. They can forge certificates, push malicious software, and impersonate services across your entire environment. Long certificate lifetimes and slow migration cycles make this even more dangerous. Design decisions you make here can stay in production and vulnerable for many years. Post-quantum cryptography is about defending against future quantum computers while still running on today's hardware and networks. Instead of relying on RSA or elliptic curves, many new schemes use lattice-based mathematics. You don't need the details yet. What matters is that these problems appear hard even for quantum attackers. NIST is standardizing these algorithms so we can gradually migrate real systems to quantum-safe security without breaking compatibility overnight. In that migration, HSMs become even more important. You can think of them as the secure cockpit where both today's classical cryptography and tomorrow's post-quantum algorithms are flown. By upgrading firmware instead of replacing entire devices, you can introduce new PQC algorithms and much larger keys, while keeping all key material inside a hardened, auditable boundary. That's what makes long-term crypto agility operationally realistic. Crypto agility means your application just says sign this document and doesn't care which algorithm actually does the work. A crypto agility engine sits in the middle, talking to the HSM. It enforces policy. Today, use classical RSA. Tomorrow, switch to a lattice-based post-quantum scheme. The change happens in configuration, not in application code. This separation lets you respond quickly to new standards, deprecations, or quantum breakthroughs, while keeping your business logic, workflows, and integrations stable. Hybrid schemes provide the practical bridge between today's systems and a quantum-safe future. Instead of replacing existing algorithms overnight, we run a classical algorithm, like ECDAE, together with a post-quantum one, such as Kyber. An attacker has to break both to succeed. This approach keeps us compatible with current protocols and regulations, while we gradually test, deploy, and harden quantum-safe options in real environments. A practical migration roadmap has 3 big moves. First, assess. Discover where cryptography is used, which HSMs, keys, and algorithms are in play, and which ones are vulnerable or business critical. Second, hybridize. Stand up test Ks, update or replace HSM firmware, and run dual-stack PKI so classical and quantum-safe paths coexist. Third, cut over. Use policy to direct new workloads to the quantum-safe stack. Gradually revoke and retire legacy algorithms, and tighten monitoring so you can catch and correct any regressions. Quantum computers will break today's public key cryptography, which puts long-lived data and signatures at real risk. Harvest now decrypt later means attackers can store traffic today and unlock it once quantum attacks mature. Your response is crypto agility. Design systems so algorithms can change by configuration and evolve HSM deployments toward post-quantum and hybrid models without disrupting the services your business depends on.